and Condren Chair of Excellence in Power Electronics at the University of Tennessee, Knoxville. He holds a joint position at Oak Ridge National Lab. He's a founding member and the technical director of CURRENT. That's the National Science Foundation Engineering Research Center. His experience also includes 8 years as a faculty member and the technical director at the Center for Power Electronics at Virginia Tech, and 10 years as an engineer and R&D manager at General Electric. His current research interests include wide bandgap device applications, power electronics and transportation grid applications, and he's a fellow of IEEE and a fellow of NAI. So with that, Dr. Wang, you have the floor.
Okay, thank you. Thanks for everyone for attending this webinar. And today I'm going to talk about the medium voltage silicon carbide-based asynchronous microgrid power conditioning system. This is sort of based on the project we are having with PowerAmerica. Since it's a relatively new project, I don't really have focus only on the project itself. I try to give some background. With a limited time, there may not be enough information provided. If you have questions would like to comment afterwards, my email is on screen here. Today I'm going to first introduce the concept of asynchronous microgrid. Most of you probably know what it is, but I give a background anyway. Just talk about the potential benefits and challenges. And then I will explain the potential benefits of using silicon carbide as part of the power conditioning system for such a microgrid. And finally, I will give a brief status update on the project itself, that is to develop medium voltage silicon carbide-based microgrid PCS system. So let me start with the introduction. By the way, if you really have questions along the way, although I know we're supposed to wait, but probably you can interrupt me. So let me go with the introduction first. This is a slide I borrowed from Al and Anand when they were talking about the distributed energy resources, and basically they have laid out the today's cases, tomorrow's cases versus future cases in terms of the penetration level of distributed generation. As you can see today, we mostly have less than about 20% of distributed generation on the grid, and the connection to the grid is not more direct through some transformer go to the medium voltage system. That is what we are doing, but often in order to increase the penetration of DG, you would have to design it in such a way that both the distribution grid and the DG themselves have to be designed together to avoid issues like power quality and also the stability. And the next step that will facilitate such a design would be using some kind of asynchronous microgrid that simply is to provide a AC-AC link that will decouple the DG or DER from the medium voltage distribution grid to make the penetration level design much simpler and better for resiliency as well as reliability and stability. And of course, in future, that decoupling link through AC-AC converter can be breaking up, even directly connected within DC link with some other sources like a battery energy storage or other load and source. So today what I'm going to focus on is really this so-called asynchronous microgrid and this AC coupling system or decoupling system. We call it power conditioning system. So this is another picture of it, and if you look at the microgrid, and this is just a cartoon with all kinds of wind, solar, and other energy resources and loads connecting to the distribution grid. And you could either do that directly like people do today, or we can do it through this AC-DC, DC-AC link and make it asynchronous. So the asynchronous microgrid, by definition, it connects to an AC distribution grid through a microgrid power conditioning system, or PCS. It will allow easier integration of renewable energy resources. It will provide better ride-through capability, either low voltage or low frequency. And also the mode transition will be easier from grid-connected mode to islanded mode or vice versa. And because of this link in between, it actually will allow the abnormal conditions such as unbalance and faults be isolated from each other between the microgrid and distribution grid. This is the example, and we have some simulation work just to show. This is an example of low voltage and low frequency ride-through and low voltage ride-through, in particular conventional microgrid versus the asynchronous microgrid. And this side shows the low voltage ride-through in conventional microgrid, and this side shows the corresponding one in asynchronous microgrid. And as you can compare the voltage for microgrid, of course, asynchronous microgrid, because it's isolated from the conventional microgrid through this PCS, the voltage magnitude, at least in this case, is very well maintained. So you will not expect a voltage drop as shown on the left-hand side. And this is the example of mode transition that is from the, let's say there is a fault on the grid side, and you would have to transition to the islanded mode. And although the grid side, you will see the voltage start to drop and power start to drop and circuit breakers start to act, but on the microgrid side, and pretty much you don't really see any changes, and the power will simply transfer from the grid to the distributed energy resources in this case, like energy storage or backup generator. So that will allow a pretty seamless transition. So here is a long list of potential benefits of the asynchronous microgrid, both the benefits and features. Most are benefits, for example, the frequency and voltage control. It will be easy for asynchronous microgrid to have the reactive power support on both sides independently, and power transfer control is also easy. On stability side, and I mentioned it can isolate stability issue, and it will enable easy integration of the microgrid, of the renewable energy resources into the microgrid. It's something I want to explain a little bit, because when you design the microgrid today, if you want to change something, like add some additional PV into it, you would have to redesign the whole thing. But when you have this decoupled link, then that design can be kind of confined to the microgrid itself. Also, for small signal stability, it can simplify the design, like I mentioned, and it can also provide oscillation damping and voltage stability. And power quality, this interface PCS converter actually can provide filtering, and that will be explained a little bit later, and that can help to save some additional filters you may need in the case of the nonlinear loads. And low voltage rise-through I already showed. And another benefit is it's easy to connect to a microgrid with multiple feeders. And the short circuit current, this may or may not be a benefit because of these converters there, and the short circuit current will be defined by the converters rather than by the loads. Of course, we add this link in between, it will cause additional loss during the normal operation, so that is something we have to take care of. And that was mainly for the grid connected mode, for islanded mode, and I mentioned the transition, and also the frequency and voltage control can be done independently from the grid side converter. Stability, the microgrid side converter can actually be a stabilizer. And same thing with power quality, and black start is also very easy. And some other benefits I already mentioned in our and our slides. Actually, this microgrid PCS can integrate energy storage and other local energy sources. And even the fault current limiting protection function probably can be integrated as well. In fact, some companies have already developed solutions using silicon technology for asynchronous microgrid. This is an example of parental energy, and in their case, they use IGBT-based approach, and the IGBT they use is, you can see the system here. They have a 3.3 kV AC system because of the limitation of the IGBTs. They use a transformer from 13.8 kV to 3.3 kV, and then that is the commercial solution. And obviously, with this, we will have to have this fairly bulky and heavy 60 Hz transformer, and the overall efficiency is also something we have to deal with. Also, because of these IGBTs are relatively slow, 3.3 kV, and you have to use some fairly higher voltage IGBTs, and they can only switch around a kilohertz or less. So some of the system level benefits are limited, the one I mentioned, because of the limited control bandwidth. So with that, we say, okay, why don't we use silicon carbide for this? So we first have analyzed the potential benefits of silicon carbide for asynchronous microgrid PCS. In particular, we like to use relatively high voltage silicon carbide, namely a few kV. An example I'm showing here is a 10 kV silicon carbide MOSFET. The benefit can be grouped into two. First is at the converter level. We have conducted some benchmark of silicon carbide-based PCS converter design in comparison with the silicon solution, the one I just showed you. And then the system level benefit includes the power quality improvement, like the harmonic filtering, stability enhancement, oscillation damping, and low voltage ride-through and transition between grid connected and islanded modes, and and also the black start. So let me start with the benchmark of the converter. And we have done basically 3 comparisons. And the first one is a baseline with the silicon. That is a similar picture I just showed with 3.3 kV AC voltage through a transformer to 13.8 kV. And then 2 silicon carbide based topology. One is a 5-level MPC, the other is an MMC. So in both cases, we have done exactly the same design for the same spec. And here is the spec we have used. Basically, it's a 1 megawatt design. So this shows different the voltages and current, and the THDs, efficiency, and also different grid support function needed, the ambient temperature, the cooling condition. And then we have carried out the design specifically for each of the architecture I have shown. So this is the silicon case, and the DC link voltage, AC output voltage, and power rating. Power ratings are the same. This is the selected devices and the switching frequency. This is really the control frequency, right? Control switching frequency, because for the MPC, the individual device switching frequency is lower. The DC cap selection based on 3% voltage ripple modulation strategy, and because of the system requirement, the filter, inductor, the transformer, the turns ratio. Similarly, this is for the 5-level MPC using silicon carbide, 10 kV silicon carbide. And so these are the results. And we actually have done 2 different designs. One is a 10 kilohertz design, the other is a 20 kilohertz design. And again, this is a control switching frequency. So based on different frequency, we have some different passive requirements. The DC link voltage is 25 kV, and we chose to have no third harmonic injection because we don't have a transformer, so we have to take care of the common mode voltage. MMC is similar, and so these are the different line parameters. And in the case of MMC, we only need to do 10 kilohertz, and we use 4 submodules per arm. Again, this is a 10 kV device. So this shows the actual comparison of the 3 different designs, actually 4, because MPC we have 2 different switching frequencies, and they all are meeting the same converter requirement. And so these are the results in terms of weight and size comparison. Okay, we have not done cost, but this is just the weight and size. And you can see the huge difference between the silicon carbide and silicon design in terms of the weight and size, even without considering the transformer, right? Transformer obviously is heavy and bulky. Even without that transformer, you can still see a huge size and weight reduction by using silicon carbide, mainly because of the switching capability it has and the lower loss. Of course, the loss in this case, we pick them to be the same. They are not the main thing. The main thing is actually the passives. So that's the converter level, system level. We look at the power quality, the system stability, and low voltage right through, mode transition, and black start. We go one by one. These are all simulation work. So we compared the silicon-based approach with silicon carbide-based approach. With silicon-based approach, because of its limited bandwidth, you would have to, if you have some harmonic load, you would have to add additional filter, either passive filter or active filter with higher enough control bandwidth, higher than what medium voltage silicon IGBT can provide. So the difference because of that is about 15% more converter rating you would have to have if you use a silicon-based approach. With silicon carbide, that can be inherently provided with very little impact on the rating, right? It's about just 1%. And in both cases, we can achieve similar PhD or TDD. For stability, we look at in two ways, and one is to connect to the grid, right? As we know, when you connect your converter to a very strong grid, probably there would be no issue. But in some cases, you don't always have very strong grid, and sometimes you may have loads that will exhibit unfavorable conditions. And with that, there could be small signal stability like harmonic resonance. And in both islanded mode and the grid connected mode, that could happen. And when that occurs, what you can do is to use control to help reformulate the equivalent impedance. But the condition for that is you would have to have enough bandwidth to do so. So here are just some comparison, silicon-based case and silicon carbide-based case. And one is switching at 1 kilohertz, the other is switching at 10 kilohertz, with exactly the same load condition. And you will see that this is grid connected mode, and the load is on the grid side. And you can see in one case, you could have the resonance. On the other, for the other case, the resonance disappears because of the higher control bandwidth available for silicon carbide. And this, of course, is for some fairly weak grid condition. It's about 10% of impedance. For islanded mode and the microgrid, the PCS will not provide power, so it's just sitting there not doing anything. So you could use it as a stability enhancer. So in this case, again, if we have some unfavorable load condition that does not match well with battery or other energy sources or PV energy sources, and assuming those sources do not have the bandwidth to deal with it, in this case, our PCS converter would be able to help with the stability as it's shown here. This is silicon-based versus silicon carbide-based case. So the low voltage ride-through, I actually already showed this earlier, and this is silicon-based case and silicon carbide-based case, and they both can ride through on the grid side, but there is a little bit better dynamic performance. Of course, on the microgrid side, it's much better because the voltage can be maintained. So if I summarize the potential benefits using silicon carbide-based PCS, asynchronous microgrid, and for the converter, huge savings in terms of weight and volume. And for the system level, it can provide harmonic filtering without adding much of capacity. And it also can help with system stability and will have better low voltage ride-through and mode transition capability. With that, let me move to the PCS converter design development itself. So this is the PowerAmerica project we are doing right now. We are a few months into it. The overall objective is to develop asynchronous microgrid PCS module using this 10 kV silicon carbide MOSFET and switching at 10 kilohertz or higher and deliver at least 100 kilowatt at 13.8 kV. And there are some efficiency targets, some density target, and also the bandwidth requirements, so it will allow us to achieve those great support function I just mentioned. And so there are actually two main tasks, and the first one is the converter hardware itself. So in this budget period, we will be developing this converter, and because of the limited resource, and this thing is expensive, right? Just material itself. So initially, we will just focus on one phase lag module and try to get all the power design taken care of. And as far as the control, those functionality I just mentioned, we will use a low voltage system to emulate those functions, and some of you may know, and at University of Tennessee, Knoxville, we have a pretty unique grid emulation system called hardware testbed. So we will be using that to actually develop the control for the PCS module and test all those functions. Because it's a really lower voltage, and we actually can switch at around 20 kilohertz, so equivalent to the higher voltage silicon carbide converters in terms of the control bandwidth. And these is actually the spec we have for the PCS we are developing. And some of the key things are really the grid-related functions, which is quite different from the regular converters like a motor drive. At this point, we have finished the device characterization. We have got all the device modules needed for the converter for the first year, and developed the gate drive, the protection, and also the isolated power supply for it. This is just an example of some of the testing we have done, the double pulse test. And this shows the gate drive, the power supply we have developed, and also just a mechanical drawing of how would the one of the sub-module will look like. And the controller have already been developed for the phase lag module, and because we already have an MMC and also other converters at UTK, we could leverage many of those. By the way, if you remember what I showed in terms of weight and size, the MGC has some obvious advantages. But on the other hand, for grid application, reliability, redundancy is a huge issue. So some modular design would be interesting and desirable. So the control we have developed so far could be used for both of these topologies. So the status at this point is we have finalized the requirements for the PCS, and especially considering the grid, and also finished the device characterization with corresponding gate drive protection and the power supply. The power stage design build is in progress. Also, the control design testing is in progress. With that, I'm thinking it's right around 30 minutes, and thank you, and I'm happy to take any questions if you have.
Thank you, Dr. Wang. That was a very interesting presentation, and we do have a few questions that have come in. I'll read them off. The first one is, how is this different from the Freedom System design using a solid-state transformer? The Freedom being the system being developed here at NC State.
Right. I don't know. I guess this is not a transformer. That's what I can see. It also has some different topologies, right? I think, I would say they are different. Yeah, but of course, some of the basic technology like high voltage silicon carbide use, they are similar, right? So we obviously do try to learn what Freedom has done, and this is not something we do it just claim we are the first one to do it. Right. So I think as far as this high voltage silicon carbide application, there are many things that can be, there's still a lot of work that can be done. So the more people working in the area, the better. I don't think we are duplicating things that Freedom is doing.
Okay. The next question is, what is the MOSFET junction temperature under normal operating conditions?
Okay. In our design, we chose 125 degrees C as the limit. Yeah. So it can be designed higher, but we chose to use 125.
Thank you. The next question is silicon carbide MMC converter capacitor weight. Could you please comment why it is about 2.5 times the silicon IGBT converter as depicted on slide 19?
Yeah, the silicon carbide IGBT is not, I suppose it was regarding to this slide I was showing, right? Because that is MPC versus MMC, right? So MMC, as we know, do require more capacitor. That's one of the drawbacks of the MMC if we don't do anything special. So that's why there are different topologies, and MPC is better in terms of the capacitor requirement, even for silicon.
The next question is, compared with a 3.3 kV system, the 10 kV system will have more clearance or creepage. How is it considered in the volume per unit of power density calculation, or the power density calculation?
Right. Yeah, obviously that's a challenge. So when we do the higher voltage one, there have to be different requirements, which is not really different from the silicon system if we go to higher voltage. So in our case, we have considered them. For example, our inductor design have a different insulation requirement, the VPI, and all that. In fact, will make the inductor quite a bit heavier and larger. But I feel this is something when we go to higher voltage, the things we have to consider. So that's the type of research worthwhile to work on. So yes, it is something that has to be considered. It's relatively new. If you talk to people who have being in the field, it's not that much experience available, really. So we are also learning how to do it right.
Okay. The next question is, on the gate driver isolated power supply, what is the capacitive coupling value what value do you recommend? And also, are you using a PCB-based transformer? So 2 questions in one.
Yes, it's around 2 pico.
And so 2 picofarads.
Right.
And are you using a PCB-based transformer?
We actually have 2 designs. We tried both, one PCB, one non-PCB, and they both could work. And so we will try to compare them. And so, yeah.
Okay, the next question is, for static applications, is power density more important or is cost more important? I think he may mean stationary applications.
Right. Yeah, you're right. I mean, of course, cost is more important. In fact, I don't really care too much about power density, to be honest with you. This power density here shows it's kind of indicating some cost. Yeah. It's because we don't really, this project, there was no cost requirement, so we don't use it as a metric. But to me, power density means cost in this case.
Okay.
Yeah.
All right, the next question is, to achieve 20 kV DC bus, is the speaker building a 5-level converter using 10 kV silicon carbide MOSFETs?
Sorry, I didn't quite get that. Can you repeat?
Okay. To achieve the 20 kV DC bus,
right,
are you building a 5-level converter using 10 kV silicon carbide MOSFETs?
Right, it's not 20 kV, right? It's 25 kV. Yeah. That's why we use 5-level. The reason for that is we cannot use third harmonic injection in this case, so we have to leave some margin for it.
Okay. The next question is, can you elaborate on the protection scheme you mentioned?
This protection is simply the desaturation. So basically, it's a desaturation protection we are using for the silicon carbide devices. Yeah.
Okay. Are there any commercial examples of MMC using IGBTs?
Of course, all MMC, to my knowledge, use IGBTs, right? So I'm not sure this was a question, though. Maybe the person is asking something else. Maybe he was referring to lower voltage or something. I don't know. I think all MMCs today use IGBTs.
Okay. All right. I think I've asked all the questions that were typed in. We have a little bit more time, so if anyone wants to unmute themselves, I'll begin to do that manually and ask a question verbally. Please do. All right. Are there any last questions for Dr. Wang? Any more questions at all? Going once? Going twice?
He gave you a list of references. I called them all. Betsy's were.
I think we're just getting some background noise.
Some undertone of something going on, like something a little funny. And then I spoke to his boss's boss in Germany, and it was also clear.
Okay, someone's having a background conversation online.
You want a guy that'll push a piece of paper from one side of the table to the other.
So I don't think there are any more questions, Dr. Wang.
He's fine. He likes sort of thinking about that person. But if you want somebody to close business, he's not your guy.
Okay, there's the ascending speaker. All right, thank you very much, Dr. Wang. I really appreciate it, the extra effort in making yourself available today, despite being on travel. And thank you all for participating in today's webinar. Have a great day.
And a great week.
Okay, bye.
Goodbye.
Okay, pretty decent attendance. Yeah, temperature for the folks. I just finished my 90-minute phone call. And